Steel is responsible for 7 to 8% of all global emissions. Every skyscraper, every bridge, every car. And for 2 centuries there was no clean way to make it. The chemistry made coal unavoidable. There is now a process that makes identical steel using nothing but hydrogen gas. No coal, no carbon dioxide, just water. If it scales, it could be one of the most consequential industrial shifts of the century. Here is how it works. Iron doesn't come out of the ground as pure metal. It comes out as iron ore, iron oxide, essentially rust locked in rock. To turn that ore into usable iron, you need to strip away the oxygen. That process is called reduction. For the last 2 centuries, we have done that reduction with coke, a purified form of coal. You pile iron ore and coke into a blast furnace, blast it with hot air, and the carbon in the coke reacts with the oxygen in the ore. The oxygen leaves as carbon dioxide. The iron stays behind. It works. It has worked at industrial scale for over 200 years. Coal currently meets around 75% of the steel sector's total energy and feedstock demand. The problem is that every ton of steel made this way releases enormous amounts of carbon dioxide directly into the atmosphere. There is no way to make blast furnace steel clean. The carbon isn't incidental, it is the chemistry. Coal is not just the fuel, it is the ingredient, which means if you want clean steel, you need a completely different process. Enter hydrogen. Hydrogen can serve as a reductant to remove oxygen from iron ore, just like carbon does, but instead of producing carbon dioxide, it produces water. H2 goes in, H2O comes out. The iron stays behind. The process is called hydrogen-based direct reduction, or H2DRI. Hydrogen gas flows through a furnace filled with iron ore pellets. The hydrogen strips away the oxygen. What remains is sponge iron, a porous metallic solid. That sponge iron then goes into an electric arc furnace where it is melted and refined into steel. If green hydrogen is used and the electric arc furnace is powered by clean electricity, carbon dioxide emissions can be reduced by over 90% compared to traditional steel making. Both conditions matter. The chemistry handles the carbon in reduction, but the electricity running the arc furnace needs to be clean too, or emissions just shift upstream. Get both right, and you're looking at a near complete elimination of one of the largest sources of industrial carbon on the planet. And the steel at the end of that process? Identical. Same strength, same properties, same steel that goes into buildings, bridges and cars. Buyers cannot tell the difference, though robust certification systems to verify and trace green steel from mine to buyer are still being developed. And this isn't theoretical. Steel made this way already exists. So if the chemistry works, why isn't the world already doing it? The answer isn't a scientific problem, it isn't even really an engineering problem. It is a race. A race between falling costs, rising investment, and an industry that has operated the same way for 200 years. Green hydrogen, hydrogen produced using renewable electricity to split water, is still expensive. You need a lot of it. Producing a single ton of iron requires at least 54 kilograms of hydrogen, and global steel production runs to nearly 1.9 billion tons a year. The hydrogen supply that would be required does not yet exist at scale. The honest comparison to solar and wind only goes so far. Hydrogen faces challenges. Those technologies did not. It is difficult to store, it loses energy at every conversion step, and it requires entirely new infrastructure from production to delivery. The analogy is not perfect, but there is a specific reason to expect costs to fall anyway. Electrolyzers, the machines that split water into hydrogen using electricity, are following their own learning curve. As manufacturing capacity grows, costs tend to fall. Renewable electricity has already fallen by over 90% in the last decade, and continues to fall. In some parts of the world, solar electricity is now the cheapest form of energy ever produced. The inputs are getting cheaper, The machines are getting cheaper. Green hydrogen is getting cheaper with them, though electrolyzer cost projections have repeatedly proven optimistic, and the pace of that decline remains genuinely uncertain. Current green hydrogen costs sit at roughly $4 to $7 per kilogram. Most models suggest that $2 per kilogram, widely seen as the threshold at which green steel becomes broadly competitive, is reachable in favourable locations within this decade. That is not guaranteed, but the trajectory is real. The question is not whether costs fall far enough. It is whether they fall fast enough before the window for industrial transition narrows. The road has not been smooth, and the setbacks are worth taking seriously. ArcelorMittal has pulled back from hydrogen steel plans at 2 German sites, citing high electricity prices, weak steel demand, uncompetitive hydrogen economics, and insufficient policy support. The economics stopped penciling out when European energy prices spiked, steel demand softened, and government subsidies did not materialize at the level the industry needed. That is not a story about technology failing, it is a story about what happens when the policy environment and market conditions shift under a long-term investment. In the United States, federal support for green hydrogen has been cut. The hydrogen production tax credit introduced under the Inflation Reduction Act has faced implementation delays and political uncertainty. For an industry making 30-year investment decisions, that instability matters enormously. And then there is Stegra, formerly H2 Green Steel, building what would be the first large-scale hydrogen steel plant on the planet in Boden in northern Sweden. As of March 2026, Stegra needs to raise more than €2 billion to complete construction, more than double its previous estimate. The plant is 60% complete. The company has reshuffled its board, added a restructuring expert to its directors, and is racing to close a financing round. The risk of insolvency has been discussed at board meetings. Citigroup has moved the company into its workout division. The Swedish government has indicated it is unlikely to provide additional support. And yet the plant keeps being built. Existing investors, including High24 and Just Climate, have stepped up with fresh capital, and the company continues to secure new commitments. The order book remains strong, with customers including Mercedes-Benz, Porsche, Scania, IKEA, and Microsoft. The question is not whether the technology works. The question is whether the financing closes before the money runs out. Stegra is the clearest example of what the transition actually looks like in practice. Not a clean leap forward, but a grinding, high-stakes race between construction progress and capital markets. If it makes it, it reduces the risk for every hydrogen steel project that follows. If it does not, it sets the timeline back by years. That tension, proven chemistry, uncertain economics, is the defining challenge of the next decade for this industry. And yet, the green steel revolution is not waiting for perfect conditions. It has already started. The most advanced example is Hybrid, a joint venture between Swedish steelmaker SSAB, mining company LKAB, and energy company Vattenfall. The partnership began in 2016 and built a pilot plant in Luleå. In 2021, they produced the world's first fossil-free steel using hydrogen reduction and delivered it to Volvo Group, which used it to build the world's first vehicle made with fossil-free steel, an autonomous electric dumper designed for use in mining and quarrying. Real machines, real work, made with near-zero emission steel. The pilot ran for 6 years, producing more than 5,000 tons of hydrogen-reduced iron. SSAB is now converting its Oxelösund plant to electric arc furnace production using a flexible mix of hydrogen-reduced sponge iron and recycled scrap, powered by fossil-free electricity. The new furnace is targeted to be operational in early 2027. The larger Luleå mini-mill, built around full hybrid hydrogen reduction at 2.5 million tons a year, is targeted for startup at the end of 2029. The Rahi plant in Finland follows as the next step. Hybrid is not alone. ArcelorMittal and Salzgitter are moving down this path despite the headwinds. And ThyssenKrupp in Germany is building an entirely new hydrogen direct reduction plant at its Duisburg site, capable of producing 2.5 million tons of DRYNT a year, targeted for completion by the end of 2026. Construction is proceeding, though ThyssenKrupp's hydrogen procurement tender has been suspended after bids came in far higher than anticipated. A reminder that building the plant and securing the hydrogen to run it are two separate problems. Stegra, if it closes its financing, is targeting production starting in the second half of 2026, scaling toward 5 million tons per year by 2030. The momentum is real. The investment is real. The steel is real. The International Energy Agency projects that 44% of iron production will be derived from hydrogen-based processes by 2050. Bloomberg NEF puts the figure at 64% in their net zero scenario. These are modelled projections, not predictions. They depend on policy support, falling costs, and capital continuing to flow. But the direction every serious model points is consistent. A wholesale shift toward hydrogen steelmaking is central to any credible path to net zero for heavy industry. That shift may also redraw the map of where industrial power sits in the world. For 2 centuries, steelmaking power has followed coal. Britain industrialised first because it had coal. Germany, the United States and China, the great steel powers, built their industries on top of coal deposits. The geography of coal-shaped industrial civilization. Hydrogen breaks that link entirely. The new inputs are sunshine and iron ore, and they are not distributed the same way coal was. Australia has some of the world's largest iron ore deposits and some of its highest solar irradiance. Brazil has vast ore reserves and enormous renewable energy potential. Nations across the Middle East and North Africa have essentially unlimited solar resources and are building the infrastructure to turn that sunshine into green hydrogen at scale. These countries are not positioning themselves to make steel, they are positioning themselves to make the ORO and ship it to wherever the steel-making capacity exists. You do not need to build a whole steel industry. You just need the ore, the sunshine and the electrolyzers, then you ship the sponge iron. Countries that have never had a steel industry may find themselves at the centre of one, not because they have coal, but because they have sunlight. The decoupling of iron making from steel making is one of the most significant potential shifts in global trade in a generation. It is slow and uncertain, but it is already beginning. There is a broader point here that goes beyond steel. Steel is what economists call a hard-to-abate sector. It requires chemical reduction, extreme heat, and processes that have no simple clean equivalent. If hydrogen can crack steel, the lesson is worth sitting with. The answer to hard-to-abate industries does not have to be carbon capture or endless offsetting. Sometimes it is a different molecule entirely. Cement accounts for another 8% of global emissions. But cement is a harder problem. When you heat limestone to make cement, the carbon dioxide does not just come from the fuel in the kiln, it comes from the limestone itself, a chemical decomposition that releases carbon, regardless of your energy source. That process emission accounts for roughly half to 2/3 of cement's total carbon footprint. Hydrogen can replace the fossil fuels in the kiln. It cannot eliminate the chemistry of limestone. Researchers are working on alternative cement chemistries, materials that achieve the same binding properties without the same process emissions. None are yet proven at the scale or cost of Portland cement. This is genuinely unsolved in a way that green steel is not. Glass and ceramics face similar but narrower challenges. Steel is the proof of concept. The template it offers is not that hydrogen solves everything. It is that every hard industry deserves the same rigorous search for a different molecule, a different chemistry, a different process. The building you are sitting in almost certainly contains steel made with coal. The rebar in the concrete, the beams in the frame, the brackets, bolts and fittings hold it all together. Every piece of it carries a carbon footprint baked in at a blast furnace. The next generation of skyscrapers may be built without burning a single ton of coal. The bridges going up in 2040 could be made from iron reduced by hydrogen, powered by solar panels produced in a country with abundant sunshine and ore. For more than a century, steel was born in coal and fire. The next generation may come from something far simpler: hydrogen, water, sunshine. If you want to go deeper, the HYBRIT project in Sweden is worth following closely. Stigra and ThyssenKrupp's TKH2 steel project are both worth watching too. I will link further reading in the description. And here is the question I want to leave you with. Steel was supposed to be permanently dependent on coal. It isn't anymore, or at least it doesn't have to be. Cement, chemicals, glass, the industries that build everything around us are next in line. The question is whether the financing, the policy and the will hold long enough for the chemistry to do its work. Drop your thoughts in the comments.